All yours, Mark.
Excellent.
Nice session. Bye-bye.
Thank you. All right, so we're going to take a bit of a walkthrough of what happens when you turn on your cell phone and you want to use your cellular data. That's basically the premise for this week. So there's a lot of work that goes on behind the scenes that allows you to be able to access the internet through your cell phone. And there's a lot that the cell phone carriers and the companies have to do, and a lot of infrastructure and costs that they bear in the background. So you know, while we as consumers, you know, you say, well, I just want to be able to watch YouTube. I want to have a good experience. I want it to be fast. The cellular data carriers, the companies, their costs are, you know, continuing to grow. We're still exploding on the overall usage of cellular data. 5G is going to help make that even easier to access data, or make it grow even faster. The backhaul costs. Okay, so backhaul is the term that's given to the fact that the cell tower has to drive itself and has to have a path basically all the way back to the carrier's sort of central data centers and central offices to be able to reach the internet. And so they've got to go all the way through this infrastructure, go out to YouTube, pull your video down, bring it back through their infrastructure and deliver it to you. So management of all of this is expensive, and having to roll a truck and go out to a cellular data site like the radio or whatnot is even more expensive if something goes wrong. So what we're wanting to show here is how open source MANO can help with the management and orchestration of all of this. Some terms that we're going to be using this week. We've got the Evolved Packet Core, or EPC. That is a term that was brought, basically that's being used to define the cellular data control and data planes. So the 3GPP consortium has got together and they've defined more acronyms than you could possibly imagine. And as this week goes on, we may throw out some acronyms here and there that we may not have introduced properly beforehand. So I just want to say, feel free to ask in Slack or in the chat. We prefer Slack because once we close the session, like say for the break, or if you join, like if you leave and rejoin, you will lose the chat. So Slack is persistent, so that's why we'd prefer if you ask the questions in Slack. But feel free to ask anywhere, and we'll get a definition to you as quickly as we can. So what does a cellular data path look like? Over on the right here, we've got UE, or the user equipment. That's your cell phone. It attaches to a radio, which then goes through a software-defined network, basically. It goes through a series of networks to get back to the Evolved Packet Core, which is what we call the P gateway, or packet gateway, basically. So it goes through there. We're going to have a web cache and a router, and then it goes out to the internet. So there's a fair amount of components in between here that allow your cellular data to travel through. So let's break this down a little bit with a couple definitions of what we're going to be seeing. So today's cellular data core, the Evolved Packet Core, is being brought to you by Facebook's Magma software. And they took a handful of functions that belong inside the network, the mobility management entity, the serving gateway, and the packet data network gateway. And they combined it, here we go, another three-letter acronym. They combined it into what they call their access gateway. So going back, sorry, let me go back here to this picture. This entire piece here that we see was a physical series of computers at one point, and the movement right now is to change this all to virtual and do it all in software. Now, it's still going to be physical computers, but they're not going to be purpose-built appliances anymore. So the goal is to replace all of these hardwired, custom-built appliances with software. So this entire thing here is what we call Magma. So we can refer back to this later on in the week, because as we start to break Magma down into its various pieces and the functions that we need to configure on it, we'll refer to like the MME and such. So this slide deck is available, as Sylvia posted in the Slack chat, as to where the presentations are. So we can refer back to this one if we need sort of a glossary and whatnot. I already described what the UE is. That's the cell phone. And we are going to be emulating our cell phone in software. So we're not, sending everybody a free cell phone, as nice as that would be. We're actually going to be launching a VM that is going to emulate the cell phone, as well as emulate the radio that the cell phone attaches to. Now, this is actually going to be using the real signaling that a cell phone would use. If you wanted to dive into it and take a look, you would see that it's actually doing all the signaling that would occur over the radio or over the air, but it's just doing it over a TCP connection instead of a radio link. So it's pretty interesting software. So going back to the cellular data path. So we said we're doing all of this in software now. We've got the UE, the eNodeB, the network, the cellular data core. There's going to be a web cache, a router, and the internet. On top of all of this, and managing all of it, is going to be open source MANO, because this is all software. And we don't want to have people driving out all over the place and installing software or changing cables if things go wrong, configuring things. We want to be able to do this from a central place and manage it all centrally. So the first thing we're going to do is we're going to be replacing in the regional data center all of the physical appliances that were there. We're starting them up with OpenStack and Kubernetes. And inside of that, we're going to be showing how OSM can deploy the Magma orchestrator as a series of Kubernetes network functions. And we're going to show how it can deploy the core itself. I should say the Magma orchestrator is something that it's a management interface for Magma, and the VEPC is the software that actually does the switching and performs all the network data path, basically. So we're going to be deploying this VEPC as a series of VMs. Over here, the radio and cell phone are also going to be deployed as virtual data units, or VMs. Our router, what would a good network be without some legacy hardware? This router is going to be what we call a physical network function. Our IT, using our pretend scenario, our IT department and security group said, nope, we're not ready to move to this new virtual world of yours. our security infrastructure is in place, and we have physical router that acts as our firewall and gateway, and we trust it, and we don't want you to change that. So you're going to need to figure out how to make your fancy OSM work with our physical infrastructure. So not only are we going to show how OSM is capable of deploying shiny new Kubernetes containers and somewhat new and a little bit dated virtual functions on VMs, but we can also show how it integrates with legacy equipment, such as a firewall that has been in place and is tried and true. So this is what you would call a brownfields implementation, where, hey, you got to deal with something that's already in place. It's not all new. So reality is messy and mixed, because we're going to have to deal with existing things, perhaps some new VMs, perhaps some mix of Kubernetes. There's going to be different networks tying these things together. There's going to be different ways of accessing these things. You're not going to be able to use, kube control to be able to talk to a physical network function. There's going to be different things going on all over the place. And we need to be able to work with each of these environments. So what we have is, with OSM, we're carving out a space for code to live that is going to bridge the gap between the virtual network descriptor and the actual function that's running out in the data center. And we call this ops code. We call these charms. So the charms actually comes from there's an entire development ecosystem out there where there's like a charm store, much as there is for other automation things such as Ansible or Salt. All of these automation systems and ecosystems have their own, places where developers can sort of meet, discuss ideas, share code, and OSM leverages the charms, which are backed by Juju. If we can take a look at that in a little bit. We'll be diving into that a lot more. But all of these things, we carve out a space inside of a container that OSM manages. The code lives in here, and it's capable of talking to the various functions. So rather than having to do anything on this old firewall, this physical firewall that was in place, we're going to have a spot where we write our code that is managed via OSM, and it's able to manage the PNF for us. So we're going to get a consistent etc interface from Sol 5 or where, the various specifications that we adhere to, going to be able to have the glue to talk back to your legacy functions, and then you're going to be able to have the legacy function be unaware of the fact that it's being managed. The same thing can happen for virtual network functions, as well as you can have this code run as part of the native, as part of the network function directly, as what we call a native charm. So if you don't want to have this arm's length management and you have access to the source or the building process of the network function, you can bundle this ops code right into the virtual network function. And the same is true for Kubernetes. It's the same pattern over and over again. So at the end of the day, it does not matter if it's a physical function, an OpenStack VM, or a Kubernetes KNF. OSM can treat all of them the same and manage them all consistently. So what is orchestration? It is that last mile configuration that needs to be done. It's how do we get that piece of software that we just deployed, how do we get it set up inside of the network so that it knows where to find other things that it needs to talk to, file changes or integration, or perhaps setting up backups or whatever. And OSM does this through what I said, things packaged as a charm. Proxy charms, as I mentioned, are run in a different execution space than the thing that it's controlling. So it has its own container that it runs in. That container can be on the same host as OSM. It can be on different hosts. It really depends on how you set your OSM up. Versus native charms that are actually inside the network function. So this would be software that you would install as part of the virtual network function. So what is this week going to look like? We are going to show proxy charms. As I mentioned, for the physical router, we're not actually going to be installing any software on our Vias router. It's pristine, and our IT department says, here is how you talk to it through its API, and you will do nothing else but talk to it through its API. So we create the proxy charm for that. For our web cache, which is backed by a piece of software called Squid, we're going to be demonstrating a native charm. So for the web cache, we're building a Docker container for Kubernetes that contains both Squid and the orchestration software that we want. And we'll get into details on that this week. For the VEPC, again, as a VM, we're going to be showing this working with a proxy charm. So we're not modifying any of the Magma software that's being deployed or being packaged and sent out as part of Magma. We're going to talk to it at arm's length by having just our proxy charm. And for our eNodeB and cell phone, because we built this ourselves, we're going to be showing how we inject the code for a native charm to be in this. So we're going to be showing native and proxy charms talking to physical appliances, Kubernetes appliances, and virtual machine appliances. Sorry, I jumped ahead of myself a little bit when I was talking about charms and the overall ecosystem that packages this up, that backs this up. So as an example, all of the various components of OSM happen to talk to each other through a message bus that is provided by Apache Kafka. So OSM itself uses upstream components, and it can use charms to deploy these upstream components. So when it comes to installing OSM with the charmed ecosystem, the charm for Kafka, as an example, is pulled right from the upstream ecosystem, and OSM didn't write any of that glueware. So what does a charm provide? Installation, configuration, update, remove, scale in, and scale out. So these are some important events when it comes to sort of providing dynamic scaling. As your load increases on functions, you may want to be able to say, okay, I need to scale from having just one front-end web server to having 2 of them or 3 of them because I'm getting more and more traffic. They can also provide integration in terms of relations. So you can have 2 components that have a relation with each other and not have to tell each one where the other is. Let me put that in context. The radio that we're going to be deploying, if I go back here, keep on missing my button. So this radio here, in this VDU, the Magma VEPC, they need to know where each other is. When the radio comes online, it needs to register with the packet core so that it can say, hey, I'm ready to serve traffic to cell phones, and I need to prove that I'm here and that I am who I say I am. So the relationship between the piece of software that is providing the core and the piece of software that's providing the radio says my IP address as a radio is 1.2.3.4, and when the EPC is deployed, it's going to say my IP address as a core is 4.3.2.1. And because each of these pieces of software has a relationship with each other, when they come up, they're going to advertise, hey, I have, I provide this end of a relationship with this data. And when the two of them come up, they will be able to perform an exchange of information. And then we don't actually have to tell the software where its peer is. It will be provided by OSM. The same thing can actually be true when you do things like databases. You can have the database create its own random password for users, and then when it's available, say, I can provide, random password X. So that way, a database and an application don't have to exchange, you don't have to generate the password outside and push it down into the software. Okay, going through the week overview, OSM is going to create and configure a combination of Kubernetes and VMs to provide the Magma functions. One thing that'll happen later this week, we're going to show how OSM can manage SRIOV, CPU pinning, and huge pages. These are lower level functions for hardware acceleration. Yes, so the information that we need to be able to provide and orchestrate the Magma gateway, there's a bunch of information that's going to be needed. And we're going to show how proxy charms basically are capable of providing all this information. The physical network router, it already exists in our network. We're not going to be deploying this. All we're going to be doing is letting OSM know where to find it. And then we're going to be configuring permit deny rules inside of it so that we can allow traffic from our trusted gateway out to the internet. The radio and cell phone, it's basically going to it's going to look like a VM, and we can access it in one of two ways. One, we can log into OpenStack and launch the console directly from OpenStack, or we can talk to it using a VNC. Whatever you end up being more comfortable with and whatever works for you. And I have included a link to the upstream software that we're using in case anyone's interested in how this software is managed. So this was a VM that we created, and it's got all this software that we built inside of it. And it will have charm code inside of it directly. Because we built this image, it's got everything we need inside of it. And so this will be shown using a native charm. Oh, I jumped ahead of myself here with the native orchestration charm, sorry. So the information it needs to know is, well, what's the IP address of the core? What are the parameters for the radio? And what are the encryption keys and identity of the cell phone? So these are things that we're going to be able to provide or have OSM provide automatically as part of the deployment. The web cache is quite simple. Simply based on Squid. Again, this container is something that we built just for this Hackfest. So all of these resources will be available as well online, and we'll be able to give you pointers to where to find all of this if you wanted to end up pulling any of these components into your own environment. So to go back, here is our big picture, putting it all together. This is what you're going to end up seeing. We're going to have our one subnet here, which is going to be for the evolved packet core. We're going to have an interface out to the physical router. It's going to be talking with Squid, which is going to cache content from the internet for us so that we don't always have to fetch the same YouTube video over and over again. All of this is going to be managed by the Magma orchestrator. Sorry, not all of this. All of the Magma components are managed through the Magma orchestrator, and OSM is going to be tying all of this together. Later, you're going to hear references or see references in networks to an S1 network and an SGI network. These networks, these names were chosen and have been put together by the 3GPP spec on cellular data networks. So these are standard networks. If you decide to look up the specifications and give yourself some lovely nighttime reading, you're going to see a whole bunch of these acronyms and crazy network names all over the place. And so we are, adhering to, like, this is a real packet core, and if you had a real radio and a real cell phone and you pointed it to the Magma VEPC, it would work. There's one other concept to introduce, and that is the overall concept of a network slice, which is a series of functions that are all tied together that are going to be deployed and managed sort of as a unit. Now, when I say managed as a unit, each individual part of it can be managed independently, but we are tying all of this together to basically say, one shot, lay all of this information down at once. I already did describe the cell phone and how you can log in using VNC or the Horizon dashboard. If you're logging in with the Horizon dashboard, the desktop credentials are here, and when the time comes, we'll be able to share, like, remind you of all this information and give that to you again. User provisioning. So the cell phone, our software cell phone, has a SIM card in it, a pretend SIM card that has credentials in it. So we need to provision that SIM card in the carrier inside of Magma. So that is going to happen as what we call day one, or part of the initial software installation. And then on day two, or on demand, or anytime we want it to happen, we have operations that can start the radio or stop the radio, and register the cell phone on the network or take the cell phone off the network. So we're going to show how OSM can do operations on, day zero, which is, oh, I need to install software. Day one, which is, okay, everything's up and running, but I need to do some configuration here. And day two, which is, literally day two and onward, ongoing care and feeding of a network where you want to be able to, add more and more users to the network, or, register and deregister cell phones on the network. So this is it. The next 3 days, actually, today plus 3 more days, or the next 4 or 5 days, we're going to be going through all of this bit by bit and breaking all of this down. So there's going to be in-depth focus on various parts of this. I actually find this really interesting. I find it quite exciting, and we're here for you all week. Ask questions, share, and enjoy.